If your tolerances are tight and your patience is tighter, you're in the right place. Let's make mechanical engineering simple, or at least mildly tolerable.
I like that. Mildly tolerable is a good goal.
Right. Well, welcome to this custom deep dive, you guys. Today's mission is, well, it's to unpack a dense, heavy, and frankly, pretty intimidating text.
Oh, absolutely.
Yeah, we're looking at Chapter 7 of an advanced dynamics textbook, which is titled Dynamics of a Rigid Body. And our goal today for you, the listener, is to look past those, formidable walls of calculus and extract the actual physical reality hiding behind the equations. We are going to demystify the physics of how things move, spin, and tumble in three-dimensional space.
And it is just a phenomenal chapter to analyze because, the mathematics of movement is something we all intuitively experience every day, but we rarely stop to actually decode it.
Yeah, exactly.
I mean, we feel these forces when we corner too fast in a car or watch a storm roll in, but seeing the actual architecture of those forces laid out on paper, it completely changes how you perceive the physical world.
It really does. So today, we're going to explore everything from the foundational rules of motion to the hidden mechanics shaping hurricanes, right up to the modern nightmare of trying to steer a tumbling satellite in the vacuum of space.
It's quite a journey.
It is, which is exactly why we need to build a solid foundation before we start launching things into orbit. The text spends a lot of time at the very beginning establishing the ground rules of movement. And it starts by setting this really firm boundary on what we're actually allowed to look at.
Right.
The chapter is explicitly about the dynamics of a rigid body. Now, in the context of advanced physics, we have to define our terms. What makes a body rigidly defined?
Well, it's a very strict definition, and it's arguably the single most important simplification an engineer can make. The textbook defines a rigid body as an object with finite volume, mass, and shape that remains entirely unchanged during the whole period of observation.
Unchanged, completely.
Completely. The distance between any two given points inside that object will never, ever change, regardless of what forces you apply to it. Deformation is just strictly off the table.
So we are pretending that bending, flexing, stretching, or squishing simply do not exist.
We have to. And I mean, it is a pretense, right? In reality, absolute rigidity is a total myth. If you take a massive steel I-beam and hit one end with a sledgehammer, that beam deforms.
Steel.
Oh, yeah. A microscopic acoustic shock wave actually ripples through the steel lattice at the speed of sound, compressing and expanding the metal as it travels.
Wow, okay. But if we were trying to calculate, say, the trajectory of a spacecraft docking with the space station, and we also had to simultaneously calculate the microscopic acoustic flexing of every single titanium strut and aluminum panel while it was spinning.
The math would just completely break down.
Right, it would be impossible.
The computational load would be unfathomable. The equations would become so nonlinear and coupled that you just couldn't extract a usable trajectory. So engineers make a calculated compromise.
A very useful compromise.
Exactly. For the sake of plotting orbits or calculating the gyroscopic forces of a spinning turbine, modeling the object as a perfectly rigid solid is incredibly accurate for the macro-scale motions we actually care about. We ignore the microscopic flex to salvage our ability to predict the macroscopic path.
Okay, so once we have this theoretical, unbreakable, unbendable object, the next challenge the text tackles is simply describing where it is. We can't just say it's over there.
No, we need precision.
Right. The text states we need exactly 6 degrees of freedom to specify a solid body's position in space.
Yeah, that is the minimum requirement to lock an object into a three-dimensional grid. It helps to visualize this in 2 separate phases. First, you have to find the object in the room.
Dislocate it.
Right. We typically choose a single reference point on the object, usually its center of mass, and we map that to a coordinate system. You need 3 degrees of freedom for this, your X, Y, and Z axes, forward and backward, left and right, and up and down.
Okay, that pins down the center of mass. We know where the middle of the object is floating in the room. But 3 degrees isn't enough, because knowing where it is doesn't tell us how it's sitting.
Exactly, and that is where the concept of a rigid body becomes so crucial. If we were just tracking a single, infinitely small particle, 3 coordinates would be fine. But our body has volume and shape.
Right.
Think of a smartphone. It can be resting flat on a desk or standing upright on its bottom edge. In both cases, the exact center of its mass might be hovering in the exact same XYZ coordinate in the room.
Oh, right, because the middle of the phone is in the same spot, but the phone itself is tilted differently.
Precisely. To fully describe the object, we need 3 more degrees of freedom to track its rotational displacement around those 3 axes. We commonly call these pitch, roll, and yaw.
Pitch, roll, and yaw.
Yeah.
So 3 dimensions of translation sliding around the grid and 3 dimensions of rotation spinning in place. 6 degrees of freedom total.
You've got it.
That sets the stage for the first major mathematical pillar in the chapter, which is Chesel's theorem.
Chesel's theorem is just beautiful because it takes an infinite universe of chaotic possibilities and distills it into a very clean rule.
How so?
Well, the theorem proves mathematically that absolutely any motion of a rigid body, no matter how complex, can be reduced to a combination of just 2 things: a translation in space and a rotation.
Just sliding and spinning.
Exactly.
You know, a good way to visualize the physical reality of this theorem for you listening is to think about a truly miserable weekend chore. Imagine moving a really heavy, awkwardly shaped, bulky couch up a winding, narrow staircase.
Oh, the worst.
The absolute worst. You are maneuvering this thing for an hour, you're tilting the backrest over the banister, you're dragging the legs across the landing, shoving it forward, pivoting it around a really tight corner.
Right.
To your exhausted brain, it feels like 1,000 different chaotic movements. But Chesel's theorem looks at that struggle and says, mathematically, every single instantaneous movement you just made was nothing more than a vector sum of sliding the couch forward in a straight line and spinning it around its center.
It completely strips away the illusion of complexity. Like at frame 1, the couch moved laterally and rotated 10 degrees. At frame 2, it moved vertically and rotated 2 degrees.
It's all just math.
Yeah, it doesn't matter if it's a couch on a staircase or an asteroid tumbling through the Kuiper Belt. The most chaotic trajectory in the universe is always just a slide and a spin.
That's wild to think about. And then the textbook pairs this immediately with Euler's theorem, which zeroes in specifically on that spinning aspect.
Right.
Euler introduces a constraint. What if we pin the object down so it can't translate at all?
Yeah, so Euler's theorem states that if one point of a rigid body is fixed in place, the motion can only be rotational.
Well, that much is intuitive. If it's pinned, it can only spin.
Right, but the real brilliance of the theorem is what it says about multiple rotations. It proves that any number of successive complicated rotations about that fixed point can always be condensed mathematically into one single rotation about a newly calculated axis.
Okay, let's unpack this. Let's apply this to a real scenario. If I have a desk globe, right, and I spin it along its normal north-south axis,
Okay.
but then while it's spinning, I mount the whole globe on a gimbal and start spinning it east to west. And then I take the whole assembly and start rotating it diagonally. So I've compounded 3 different spins in 3 different directions all at once.
And if you try to track all 3 of those individual spinning vectors simultaneously, the geometry would be an absolute nightmare.
I can't even imagine.
But Euler's theorem proves you don't have to. The math shows that those 3 overlapping, compounding rotations physically result in the globe spinning around one single invisible axis.
Wait, really? Just one?
Just one. By repeating a logical proof that 2 rotations can combine into one Euler, showed that 50 simultaneous rotations can ultimately be expressed as one unified rotation around a single vector.
This feels like a massive cheat code for mechanical engineers designing robotics or something.
Yep. It absolutely is. I mean, consider the robotic arm on a car assembly line. It has a shoulder joint, an elbow, a wrist, and a spinning tool head.
Right.
When that arm swings around to weld a car chassis, every single one of those joints is rotating at a different speed on a different plane. If the computer guiding that arm had to independently track a dozen compounding spins to figure out where the welding tip was pointing, the latency would be huge.
The computer would just lag out.
Exactly. So Euler's theorem allows the software to take all that chaotic tumbling and mathematically synthesize it into a single axis of rotation. It vastly simplifies calculating the final orientation of the tool.
Okay, so we've established how bodies move in a static room. They slide and they spin. But the textbook quickly abandons the safety of a static room.
Yeah.
Moving into section 2 of the chapter, we confront what happens when the room itself is moving.
Yes.
This plunges us into the world of moving frames of reference and the phantom forces of inertia.
And this transition is where abstract math starts to really explain the visceral sensations we feel in our daily lives. The text differentiates between an inertial, fixed frame of reference, which it labels with capital X, Y, and Z, and a moving, rotating frame of reference, labeled with lowercase x, y, and z.
Right, capital letters for fixed, lowercase for moving. To put a picture to this for you listening, imagine standing on a train platform. You are in the fixed capital XYZ frame. The ground beneath you isn't going anywhere.
Exactly.
Now look at a bullet train speeding past you and imagine it simultaneously accelerating and entering a long curve. The interior cabin of that train is the moving, rotating lowercase ZYZ frame. If a passenger inside that train tosses a tennis ball across the aisle, calculating the math of that ball is completely different depending on whether you are the passenger or the person standing on the platform.
Bridging the perspective of those two observers requires what is known as a Galilean transformation. The textbook derives the equation of motion for a mass in the moving frame relative to the fixed frame. And it does this by looking at how vectors change over time in both systems.
Yeah, and the text gets incredibly dense here with derivatives, looking at how a theoretical vector changes in fixed coordinates versus rotating systems. I want to avoid just reading the alphabet soup of the formula, but the core mechanism relies on something called the cross product.
Oh, yes.
This term, the cross product, is going to dictate almost everything else in this chapter, from hurricanes to satellites. We need to define what that actually means physically.
It is the bedrock of rotational dynamics. When we multiply two regular numbers, say 3 times 4, we get 12, just a bigger amount in the same dimension.
Right, simple math.
But a cross product is a way of multiplying two directional vectors. If you have a vector pointing forward and another vector pointing to the right, taking the cross product doesn't just give you a bigger forward or rightward vector, it creates an entirely new vector that is perpendicular to both of the original ones.
Oh, so it pushes out of the plane, like the classic right-hand rule.
Exactly the right-hand rule.
So if you point your index finger straight forward and point your middle finger straight to the left and then stick your thumb straight up, your thumb is the cross product. Two vectors interacting on a flat plane generate a completely new force pointing straight up into the third dimension.
Precisely. And in the Galilean transformation, the textbook shows that observing a velocity from the fixed frame equals the velocity seen in the moving frame, plus the cross product of the moving frame's angular rotation and the object's position.
Okay, I follow.
And this mathematical relationship eventually leads the author to take another time derivative to find acceleration. And from acceleration, using Newton's law that force equals mass times acceleration, we finally arrive at the forces.
The text calls these the effective forces. It's a pretty long equation with 4 distinct terms that dictate the exact physical forces you feel when you are trapped inside a moving frame of reference.
And these 4 terms mathematically validate our real-world intuition. Let's walk through what a passenger on that accelerating, curving train actually feels.
Okay, let's do it. So the first term involves the negative mass of the object multiplied by the translational acceleration of the moving frame. What is that physically?
This is linear inertia. When that train driver throttles up, the train accelerates forward. But as a passenger inside that moving frame, you feel a distinct physical force shoving you backward into your seat.
Right.
The negative sign in the equation is the key here. It dictates that the phantom force you feel is always in the exact opposite direction of the frame's acceleration. Your body wants to stay put. The frame moves forward, so relative to the frame, you are forced backward.
That's the feeling of a sports car launching off the line, pushes you right into the leather. Okay, what about the second term? This one brings in angular acceleration, so how fast the frame is speeding up its spin.
Right. This term is the inertial force produced when a rotating frame changes its speed. Imagine you are standing on the outer edge of a playground merry-go-round. It's stationary. Suddenly, a group of kids grabs the bars and spins it aggressively to get it up to speed.
You would immediately feel a violent jerk throwing you backward against the direction of the spin, like you're going to fall off.
Exactly. The frame experiences an angular acceleration in one direction, and the second mathematical term, which involves a cross product, proves that you will experience a force pulling you tangentially in the opposite direction.
Okay, so that covers speeding up in a straight line and speeding up in a spin. The third term deals with a frame that is already spinning at a constant speed. The text identifies this as centrifugal force.
This is a widely misunderstood concept, but the equation defines it perfectly. The term is negative mass multiplied by a double cross product involving rotational velocity and position.
A double cross product.
Yeah, but simply put, it dictates that any object sitting inside a rotating frame will experience a continuous outward force pointing directly away from the center of rotation.
The textbook uses a brilliant macro-scale example for this. Satellites in orbit.
Yeah, a satellite moving in a circular orbit is essentially just an object trapped in a rotating frame revolving around the center of the Earth. The rotation creates that outward centrifugal force. The reason a satellite doesn't crash back down to Earth is that at a very specific velocity, this outward centrifugal force perfectly, mathematically balances the inward pull of Earth's gravity.
And this equilibrium is the sole reason astronauts experience weightlessness.
Exactly.
A lot of people assume there is zero gravity in space, which is entirely false. If there were no gravity up where the International Space Station is, it would just fly off in a straight line into deep space. Gravity is pulling on those astronauts fiercely.
Right, very fiercely.
But because they are moving sideways so fast, the outward centrifugal force, described by this third term, perfectly cancels out the inward gravity. The net force is zero. So relative to their moving frame inside the cabin, they float.
It is a delicate balance of massive forces resulting in a local sensation of zero force. It's beautiful, really.
It is. But the final term in this equation, the fourth term, is where the physics become wildly counterintuitive.
Yes, the Coriolis force. The equation shows this force only exists if you have an object that is actively moving with its own velocity inside a frame that is rotating.
So going back to the merry-go-round, if you are just standing on the edge holding on, you feel centrifugal force pulling you outward.
Right.
But if you try to let go and walk across the spinning surface toward the center, you introduce a new velocity vector.
Exactly, and the Coriolis force equation tells us that your inward walking velocity interacts with the outward rotational vector of the merry-go-round via a cross product.
And based on our right-hand rule, an inward vector crossing an upward vector creates a third perpendicular force.
Yes. As you try to walk in a straight line toward the center, an invisible force will push you sideways, causing you to curve. And on a planetary scale, this exact mathematical quirk orchestrates the most violent weather on Earth. The textbook dives into the formation of hurricanes to illustrate this.
Okay, let's talk about that. The Earth is the ultimate rotating frame of reference. So how does this mathematical cross product physically spawn a hurricane?
Let's focus on the northern hemisphere. Imagine a pocket of very low atmospheric pressure developing over the warm ocean. High-pressure air from the surrounding environment naturally wants to rush inward to fill that void.
Makes sense. Air moves from high to low pressure.
Right, so you have a massive volume of air with an inward velocity vector, but the Earth is rotating beneath it, which provides a rotational vector pointing outward from the surface.
And here comes the cross product. The inward rushing air and the Earth's rotation generate a perpendicular force.
The Coriolis force, yes. As the air rushes straight toward the low-pressure eye, the Coriolis force continuously shoves it to the right. The air tries to go straight, gets pushed right, tries to go straight again, it gets pushed right again.
Which is constantly deflecting it.
Constantly. This continuous perpendicular deflection forces the rushing air into a massive, spiraling, counterclockwise rotation around the low-pressure center.
The wind just wants to go to the center, but the geometry of the moving frame turns it into a spiral.
Exactly.
But why is it so destructive? Like, why do the winds near the eye reach 150 miles an hour? The textbook points out that rotational momentum is conserved in this system.
Conservation of angular momentum is a powerful principle. Think of an Olympic figure skater. They start a spin with their arms outstretched. As they pull their arms in tight to their chest, what happens?
Your spin drastically accelerates.
Right. The hurricane acts on the exact same principle. That massive volume of air begins its gentle rotation hundreds of miles away from the center. But as that air gets sucked closer and closer to the eye, its radius of rotation shrinks.
Because it's spiraling inward.
Yeah. Because the angular momentum must be conserved, the tangential velocity of the air has to massively increase to compensate for the smaller radius. By the time that air reaches the eye wall, its speed has multiplied to catastrophic levels.
So a stiff breeze on the outer bands becomes a Category 5 nightmare at the center.
All because of conservation of momentum.
And it all traces back to a simple cross product inside a rotating frame of reference.
Yeah.
I mean, we've seen this phantom perpendicular force orchestrate storms on a planetary scale. Let's shrink the scale down. Moving into Section 3, the textbook shifts focus from tracking entire rotating environments to tracking a single object skinning aggressively on its own.
It's time to put that force on a desk. To understand the dynamics of a single spinning object, we first have to calculate its angular velocity with absolute precision. The author presents two distinct mathematical pathways to find Euler's angular velocity.
Okay, two pathways.
The first approach relies on matrix operations. specifically applying rotational matrices to the coordinate axes. The second approach uses a rotation operator, which applies a transformation directly to the vector itself.
And the text devotes pages to these derivations. We are talking about matrices, multiplying matrices, sines and cosines of Euler angles stacking on top of each other. It's a lot.
It is dense, yeah.
But after all that heavy lifting, both methods deposit us at the exact same final equation for the angular velocity vector. From a practical standpoint, why would a textbook present two entirely different mathematical languages to say the exact same thing?
Well, it highlights a crucial transition in how engineers interact with physics in the computer age. The two methods represent a difference in perspective.
How so?
The matrix method is like trying to orient yourself by taking the map and physically rotating the paper until it aligns with the terrain in front of you. You are rotating the coordinate system to match the object.
Okay, shifting the whole world to match the object.
Right. The rotation operator method is like holding a compass and walking through the terrain. You are leaving the coordinate universe fixed and calculating how the object twists within it.
That makes the distinction much clearer. But if the result is identical, does the choice of method matter? The text mentions the rotation operator was only recently rediscovered, and its applications are still being developed.
The choice matters immensely when you transition from a textbook to a supercomputer.
Oh, because of processing power.
Exactly. A structural engineer might find that simulating the stress on a bridge is computationally much faster if the computer doesn't have to mathematically rotate the entire universe, the matrix method, every time a component shifts.
That sounds exhausting for a computer.
It is. Applying a rotation operator to just the vector of the component can save massive amounts of processing power. Having divergent methods that arrive at identical physical truths gives engineers a larger toolkit to optimize their simulations.
Okay, that makes sense. So having mapped out the velocity, the text pushes forward into the forces driving that velocity, introducing the Euler equations of motion. And at first glance, these equations look like a nightmare of crosstalk and overlapping variables.
They relate the applied torques to the changes in a body's angular momentum. The messiness comes from a body's mass distribution.
Right, because most things aren't perfect spheres.
Exactly. If you have an asymmetrical object like a rock spinning it around one axis is going to inherently cause it to wobble and pull on the other axis. The text refers to this crosstalk as products of inertia.
But the author pulls a brilliant mathematical maneuver here to clean up the mess. They introduce the concept of principal axes.
Yes. The physics dictate that every single rigid body, no matter how lopsided or strangely shaped, possesses a set of three mutually perpendicular axes where the mass distribution is perfectly balanced.
Wait, really? Every object?
Every single rigid object. If you rotate your mathematical coordinate system to align perfectly with these three principal axes, all of those messy products of inertia instantly become zero. They just vanish from the equation.
That's incredibly convenient.
It is. Suddenly, the angular momentum along the x-axis depends exclusively on the rotation around the x-axis. The Euler equations collapse into a clean, manageable set of formulas.
And to demonstrate the power of these simplified equations, the textbook brings in arguably the most famous physics demonstration of all time, the toy gyroscopic top.
It is the perfect vessel for exploring applied torque.
Let's construct the scenario physically for the listener. You have a heavy metal disc mounted on a central shaft. You pull a ripcord, spinning the disc up to a massive angular velocity. Then you take the pointed tip of that shaft and set it on a small pedestal.
Right.
The top is now leaning at an angle. Gravity is pulling straight down on the heavy disc. The disc's weight is acting at a distance from the pivot point on the pedestal, which creates a downward torque. Every ounce of human intuition screams that this top should instantly flop over and hit the table. But it doesn't.
It defies gravity entirely because of the gyroscopic effect, which is governed by the cross product inherent in Euler's equations. Let's trace the forces. We have an immense angular momentum vector pointing along the shaft of the spinning top.
Pointing outward along the tilt.
Yes. We also have the downward torque vector created by gravity trying to pull the top over.
And just like the inward air and the rotating Earth in the hurricane, these two vectors interact.
Exactly. The downward torque crosses with the spinning momentum, generating a new force that is perpendicular to both. Gravity isn't allowed to pull the top down. Its force is entirely redirected sideways.
Redirected sideways.
Yeah, this causes the entire leaning axis of the top to sweep out a slow, horizontal circle around the pedestal. This motion is called precession.
The math in the text reveals a fascinating relationship here. The angular velocity of that sideways precession is directly proportional to the torque from gravity. A heavier top feels more torque, so it wants to precess faster. But the precession is inversely proportional to the angular momentum of the spin.
Which means the faster the disc is spinning on its shaft, the slower the entire apparatus sweeps around the pedestal.
So if you spin it up to an extreme velocity, the cross product is so dominant that the top barely precesses at all. It appears to hover perfectly still at an impossible angle.
It does, but we know friction is always stealing energy.
Right.
As air resistance slows the spinning disc down, the angular momentum drops. Because of that inverse proportionality, as the spin drops, the sideways precession speed must increase to balance the math.
You can watch it happen on the desk. The top spins slower, but sweeps around the pedestal faster and faster until the equilibrium breaks down and it crashes.
It is a profound visualization of an invisible mathematical law. Gravity's downward pull is being mechanically converted into horizontal motion.
It's just magic to watch. But a toy top is light, fast, and relatively simple. Its precession is a smooth, predictable sweep. But as we transition into Section 4, the textbook scales up the complexity, introducing the heavy symmetrical top.
Oh, yes.
When mass increases, smooth precession goes out the window, and we enter the chaotic math of the wobble.
The author actually abandons the Euler equations at this point. They acknowledge that for a heavy top, especially one where the initial spin might not be perfectly horizontal, calculating the forces and torques becomes way too cumbersome.
So what do?
Instead, they pivot to a completely different framework, Lagrangian mechanics.
This is a major paradigm shift. We stop caring about forces and cross products, and we start looking at the system through the lens of energy, right?
Yes. Lagrangian mechanics operates on a principle of energy balance. It looks at the entire system and calculates the difference between kinetic energy, the energy of the top's motion, and potential energy, the energy stored by its position against gravity. The text writes out the Lagrangian function using the Euler angles we discussed earlier.
And setting the problem up this way reveals a massive shortcut.
A critical one. When you look at the energy equations, the actual angles for the top's spin and its precession, the coordinates phi and psi, don't actually appear in the Lagrangian function, only their velocities appear.
Wait, the angles themselves are missing?
Yep. In this mathematical framework, if a coordinate doesn't appear in the function, it is deemed ignorable.
Ignorable sounds like bad practice in advanced dynamics, like we're just sweeping things under the rug.
I know, but it's actually revelation. If a coordinate is ignorable, it proves mathematically that the momentum associated with that specific motion is a conserved constant.
Oh.
Yeah, it means that no matter how violently this heavy top is wobbling on the table, the total energy of the system is locked in, the momentum of its spin is locked in, and its momentum around the vertical axis is locked in.
So by anchoring the problem to those constants, the author takes this impossibly complex, tumbling heavy mass and boils all the math down into a single, solitary, nonlinear differential equation. An equation that solves for theta, the angle of the top's tilt. But there's a catch.
There is a massive catch. The catch is that this resulting differential equation is so fundamentally complex, it cannot be integrated analytically.
It can't be solved.
There is no neat, tidy algebraic formula that pops out at the end to tell you exactly what the top is doing at any given second.
This would be the point where a layperson might throw the textbook at the wall. The math is literally unsolvable. But this is where the textbook demonstrates the absolute poetry of mathematical physics. They can't solve the equation, but they can still extract physical reality by studying the shape of the equation.
Think of it like mapping a canyon in the pitch dark. You can't see the canyon floor, but if you throw a rock and listen for the echo, you can find the boundaries.
I love that analogy.
The author analyzes the boundaries of this unsolved equation by finding its roots, the points where the function equals 0. They discover 3 roots. One is mathematically impossible in real space, leaving 2 valid roots.
And what do those roots represent?
These 2 roots represent the absolute minimum and maximum tilt angles that the top is physically allowed to bounce between without violating the conservation of energy.
And this bouncing, this nodding up and down between the maximum and minimum tilt is what the text calls nutation. This secondary wobble is layered on top of the precession we already learned about. And by studying the constants for the heavy top, 3 cases of nutation.
In case 1, the mathematical constants create a scenario where the top is always sweeping forward in its precession. Physically, this manifests as a smooth, wave-like wobble. The top nods up and down between its two boundary angles while continuing to sweep a circle in the air.
So if you attached a pen to the tip of the top, it would draw a wavy sine wave wrapped around a cylinder.
Exactly. Now, in case 2, a specific constant ratio exactly equals one of the roots. When this happens, the math dictates that the precession velocity must briefly hit absolute zero right at the top's lowest tilt angle.
Wait, it stops precessing.
Just for an instant.
Yeah.
So, drawing with our imaginary pen, it draws a series of sharp cusps. The top swoops down, spikes sharply to a dead stop for a fraction of a second, and then bounces back up, creating a shape like a pointed crown.
The velocity momentarily zeroing out before rebounding is a fascinating physical manifestation of the equation's boundary. But case 3 is where the physics truly become bizarre.
Oh, yes. When the constant ratio falls between the two roots, the math forces the precession speed to briefly become negative.
Negative precession. The top is sweeping forward around the circle, but the downward nod is so violent that it forces the top to actually back up for a split second.
Yes. The axis loops back on itself. If you were tracking the tip, it would draw literal loops in the air, like a series of cursive lowercase U's arranged in a circle.
It is incredible. Depending entirely on the precise energy state when you release the top, it will either wave, spike, or loop. The textbook proved this without ever actually solving the core equation. They just looked at the structural boundaries of the math and read the physical reality off it like a Braille translation.
It's a masterclass in extracting physical meaning from incomplete mathematical information.
Okay, so we spent a significant amount of time studying tops spinning on desks. We understand the wobble. But section 5 is where the training wheels come off. The text takes all this theory, scales up the mass, and straps that spinning gyroscope to a high-speed vehicle. Let's talk about the terrifying reality of real-world gyroscopes.
Yeah, this is where rigid body dynamics elevates from a tabletop curiosity to a life-or-death engineering constraint. The textbook moves into studying gyroscopic motion inside actual machinery, and the primary example it uses is a single-engine airplane propeller.
This example is fantastic because it grounds all our theoretical talk with hard numbers. Let's lay out the scenario. We have an airplane, and in its nose is a propeller with a mass of 30 kilograms and a moment of inertia of 25 kilogram meters squared.
Okay.
It is spinning clockwise at a blistering 2,000 revolutions per minute. The airplane is flying straight and level. Then the pilot decides to initiate a turn to the right at a rate of 0.2 radians per second.
This is the exact crucible Euler's equations were built for. You have a massive spinning object to the propeller, and you are introducing a secondary rotation, the turn to the frame that is holding it.
And we know what happens when two rotations interact. The cross product generates a phantom force perpendicular to both. What does this mean for the pilot turning right?
Well, we calculate the massive angular momentum of the propeller spinning at 2,000 RPM. We cross-multiply that with the angular velocity of the airplane turning right. The resulting gyroscopic effect instantly generates a massive torque along the pitch axis of the plane.
How big is the torque?
The textbook calculates the exact value of this torque. Negative 10,045 Newton meters.
Over 1,000 Newton meters of torque just appearing out of thin air because the math demands it. But the text doesn't stop at torque. It translates that into physical stress on the metal.
Right.
The propeller shaft is held in place by bearings that are spaced 150 millimeters apart. Because of that short lever arm, that torque concentrates into a physical shearing force on those bearings of almost 7,000 newtons.
6,967 newtons of force, to be exact. And because of the geometry of the cross product, that force isn't pushing the engine block left or right. It is pushing vertically. The negative sign on the pitch axis means the moment produced by this force violently shoves the nose of the airplane downward.
So the pilot turns the steering wheel right, and the engine physically wrestles the plane into a dive.
Exactly.
If the pilot had turned left, the vectors reverse, the cross product points the other way, and the nose of the plane would pitch violently upward into a climb. Early aviators flying planes like the Sopwith Camel in World War I, which had massive rotary engines, had to learn this the hard way.
They did. Many crashed because of it.
They weren't just fighting the wind. They were engaged in a physical wrestling match with the gyroscopic ghost of their own engine. Every time they yawed, the engine pitched.
It requires intense, counterintuitive correction from the pilot. You have to apply back pressure on the yoke just to execute a flat level turn. Modern aviation relies on flight computers to automatically actuate control surfaces to seamlessly compensate for these exact gyroscopic forces.
So the pilot doesn't even know what's happening.
Right, the pilot never feels the fight, but the computer is constantly running the cross-product math derived in this chapter to keep the plane level.
That's wild. The textbook then shifts its gaze from the engine pulling the plane to the instruments guiding it. It discusses rate gyros, which use carefully calibrated springs to measure a vehicle's rotation rate, but the most profound application is the gyrocompass.
Ah, the gyrocompass is a marvel of applied physics. It is a gyroscope with 2 degrees of freedom designed to do one very specific job: find the true geographic North Pole.
Not magnetic north.
No, it doesn't rely on magnetic fields at all, which are notoriously fickle and wander over time. It uses the physical rotation of the planet itself to align its axis with true geometric north.
But the textbook immediately introduces the major complicating factor.
Mm.
The compass works perfectly in theory, but in practice it is sitting on the surface of the Earth. And as we discussed earlier, the Earth is a moving frame of reference.
Yes. The Earth rotates at roughly 7.27 times 10 to the negative 5th radians per second. To human perception, that is glacially slow. But a gyrocompass is an incredibly sensitive instrument designed to maintain a rigid orientation in space. As the Earth slowly rolls underneath it, the room the compass is sitting in is subtly tilting.
It's the moving frame scenario from section 2 all over again. The compass wants to point to a fixed spot in the absolute universe, but the floor it's bolted to is rotating.
Exactly. The text incorporates the latitude of the compass's location and the Earth's rotational velocity into the Euler equations. And the math reveals that the gyrocompass can never just point perfectly north and lock in.
It can't.
No. The slow rotation of the Earth beneath it continuously induces a tiny cross-product torque on the spinning rotor. This forces the spin axis of the compass to continuously oscillate about the meridian. It constantly sweeps back and forth across true north.
The text provides another specific calculation here. It models a compass sitting at 20 degrees latitude, with a rotor spinning at a massive 20,000 radians per second. When you crunch the numbers through the equation, the resulting oscillation frequency is 0.263 cycles per second.
Meaning the compass needle has a period of oscillation of about 3.8 seconds. Every 3.8 seconds, it swings back and forth across true north.
It is a profound realization. You can be standing perfectly still on a concrete floor holding a compass, but the immense quiet mechanics of the solar system are literally reaching through the casing and making your needle vibrate. Nothing is ever truly stationary.
That's the beauty of dynamics.
And speaking of the solar system, that brings us to the final frontier of the chapter, Section 6, Space-Age Dynamics. We've seen how airplanes fight the gyroscopes in their noses, but planes have wings and air pressure to help stabilize them. What happens when you leave the atmosphere entirely and try to steer an object in the vacuum of space?
Well, the text introduces this section with a sense of novelty, noting that the space era brings entirely new dynamics problems that are still being solved. It starts with the most foundational scenario possible: a rigid satellite orbiting the Earth in a perfectly circular path.
The first order of business is establishing a coordinate system, and the text builds an invisible scaffolding that travels with the satellite.
Right. It is a highly specific, rotating right-size Z-frame centered on the satellite's mass. The Z-axis always points straight down to the center of the Earth. The axis points forward along the orbital flight path, and the X-axis points out to the side, anti-parallel to the orbital angular velocity.
Okay, so Z is down, Y is forward, X is left. That framework orbits the Earth. But the critical piece of the puzzle is that the metal body of the satellite is not welded to this invisible framework.
No, it has to move.
As the satellite orbits, it might need to pitch its nose up, roll on its side, or yaw left and right relative to that scaffolding to point a camera or a solar panel.
And to figure out how the satellite behaves when it rotates, the author breaks the satellite down into tiny microscopic elements of mass, they call them DM, and calculates the forces acting on every single one of them. We are reunited with the inertial forces from Section 2. The text identifies 3 distinct sources of torque acting on this orbiting body.
The first is gravity. Not just the uniform pull, it's the gravity gradient.
Yes. Even in orbit, gravity is pulling on the satellite, but gravity weakens with distance. If you have a satellite that is 10 meters tall, the bottom of the satellite is 10 meters closer to Earth than the top.
Oh, I see.
Therefore, gravity pulls infinitesimally harder on the bottom than it does on the top. Over the scale of the entire body, this differential pull creates a tiny, persistent torque trying to rotate the satellite.
The tidal forces of the Earth basically trying to tip the craft.
Exactly.
The second source of torque is our old friend, centrifugal force.
As the satellite revolves around the Earth, centrifugal force pushes it outward. But just like gravity, this force varies depending on how far a specific piece of the satellite's mass is from the center of rotation. A solar panel sticking out further experiences a slightly different outward pull than the main hull, generating a second source of torque.
And the third source is the Coriolis force, which appears if the satellite is actively rotating relative to its orbital frame. If it's pitching or rolling, its internal mass elements are moving inside a rotating system, generating that perpendicular push.
Right.
The textbook wades into a massive mathematical derivation here, integrating all these microtorques over the entire volume of the satellite, accounting for its moments of inertia. Let's cut through the calculus and look at the physical result. What actually happens when mission control tells a satellite to fire a small thruster to roll slightly to the right?
Well, the math reveals a profound and frustrating reality for aerospace engineers. When you calculate the torque required to induce a pure rolling motion rotation strictly around the y-axis, the resulting equation spits out components in the I, j, and k directions.
Meaning the torque doesn't stay confined to the roll axis, it bleeds into the x and z axis.
Exactly. Because of the cross products of inertia we discussed earlier, yawing and rolling motions will always, inevitably generate torques about all three axes simultaneously. You physically cannot isolate the motion.
This is wild. It's like trying to drive a car where turning the steering wheel inherently causes the brakes to slam on and the radio volume to blast to maximum all at the same time.
That's a good way to put it.
If I fire a thruster to just roll the satellite, the physics of the orbit will instantly cause it to also pitch forward and yaw off target.
These are known as parasitic torques. The textbook mathematically proves that rolling and yawing inherently produce overlapping, chaotic rotations about all three axes.
So how is a modern satellite network even possible? How do you steer something that inherently fights your commands in 3 dimensions?
With staggering computational precision, you cannot simply fire a roll thruster, wait for it to finish, and call it a day. The flight computer has to run these advanced dynamic models continuously.
Predicting the mess before it happens.
Yeah, it anticipates that a roll command will instantly induce a parasitic pitch and yaw. To execute the maneuver, the computer must simultaneously fire opposing thrusters or spin internal reaction wheels on those other axes to perfectly cancel out the parasitic torques in real time.
Wow.
It is a delicate, multi-dimensional balancing act performed in a vacuum while flying at 17,000 miles per hour.
And just when you think you have a handle on the sheer complexity of that balancing act, the textbook closes the chapter with a deeply sobering caveat.
It does. After 20 pages of exhaustive, mind-bending calculus to map out these parasitic torques and stabilize the system, the author quietly notes a massive limitation.
The text literally ends by stating, "It is easy to recognize the need for a great deal more research for a satellite in an elliptical orbit."
Yeah, every single calculation in the space dynamics section assumed a perfectly circular orbit. But in an elliptical orbit, everything changes constantly. Your distance to the Earth stretches and shrinks. Because the distance changes, the gravity gradient changes every second.
And because gravity changes, your orbital velocity changes.
Exactly. The centrifugal force fluctuates. The math doesn't just get slightly harder, it explodes in complexity. The chapter basically opens the door, shows you the mathematical monster hiding inside space dynamics, and leaves you on the threshold to figure out the rest.
And that cliffhanger brings us to the end, Chapter 7. Let's recap the journey we took today. We started with the foundational rules of rigid bodies, learning from Chasles and Euler that every chaotic, clumsy movement in the universe is just a clean combination of a slide and a spin around a single axis.
It's all just slides and spins.
We dove into moving frames of reference and uncovered how the right-hand rule of the Coriolis force orchestrates the terrifying, counterclockwise winds of a hurricane. We discovered how a spinning top uses a mathematical cross product to convert gravity's downward pull into a sideways precessional sweep, and explored the complex Lagrangian energy balance that dictates whether a heavy top will wave, spike, or loop as it wobbles.
We covered a lot of ground.
We strapped a gyroscope to a turning airplane and proved why the pilot must physically wrestle 1,000 Newton-meters of force to keep the nose from diving. We saw how the immense rotation of the Earth reaches up to make a gyrocompass oscillate every 3.8 seconds. And finally, we ended up in the vacuum of space, realizing that the simple act of rolling a satellite unleashes a multidimensional nightmare of parasitic torques.
Quite the deep dive.
I want to remind you why we take deep dives into text like this. Engineering is so much more than memorizing formulas, machining parts, or hitting tight tolerances. It is the art of predicting the invisible forces that govern the universe. It's the audacious attempt to take the chaotic, terrifying complexity of the physical world and use matrices and differential equations to map it, to anticipate the wobble, to make the impossibly complex mildly tolerable.
The math we explored today is dense, but it is the literal source code of reality. It is the language we use to keep planes in the sky and satellites locked on target. But before we sign off, I want to leave you with one final thought to mull over.
What's that?
We have spent this entire hour analyzing the dynamics of rigid bodies, unbending, perfect, idealized shapes. But as we established at the very beginning, absolute rigidity is a myth.
Yep.
Out in the real universe, almost nothing is perfectly rigid. We just saw that simply rolling a solid, rigid satellite creates chaotic, parasitic torques in all three dimensions. Now imagine the unfathomable complexity of applying these same motion principles to the non-rigid, fluid, and chaotic bodies that actually populate space.
Oh, man.
Imagine trying to calculate the precession of an asteroid that isn't a solid rock, but a loose pile of rubble held together by microgravity, constantly shifting and redistributing its mass as it tumbles. Or look even closer to home. Imagine trying to precisely calculate the rotation of the Earth itself.
Because it's not a rigid sphere.
Not at all. The Earth is a spinning mass, but is profoundly non-rigid. Its liquid oceans are constantly shifting with the tidal pull of the moon. Its molten core flows independently of the crust. Massive polar ice caps are melting, turning solid mass into liquid and redistributing millions of tons of weight across the globe on a daily basis.
That's terrifying to try and calculate.
How do those immense internal deformations alter our planet's wobble as we fly through space? It is a staggering problem. The math of rigid bodies is a beautiful, essential foundation, but it is just the very beginning. The universe is fluid, it is messy, and it is waiting for engineers to figure it out.
Now there's something to keep you up at night. Thank you for joining us on this deep dive. Keep questioning the physics around you and keep exploring.